Hi everyone, hope you're doing well. We're going to wait for about 5 minutes for others to join us and start the workshop. See you then. Hello again. So 2 people have raised their hands. Is there anything you want to discuss?
I apologize. I thought it was a wave.
Oh, okay. Hi, anyway.
Hi, brother.
There's another person. Maybe they thought the same. All right, then. Perfect. I think we can get started. So hello, everyone, and thank you for being here today, and welcome to this workshop, which will be on object detection with deep learning. So we will have an introduction on what object detection is, and
Sorry, Ken, so I think you're on mute.
Oh, can you hear me now?
Yeah, lovely.
Yes.
Thank you.
Yeah, thank you. All right, so I was saying that hello, everyone, and thank you for being here today. Welcome to this workshop on object detection with deep learning. So as you can see on the slide, it will be an introduction to object detection. My name is Kenza Yusfi, and I am a member of the Teaching Assistants in Code Labs Academy, and I will present this workshop and help you get the most out of it. So just to help me out with maybe internet connection issues, I'm just going to disable my camera during the workshop. Feel free to write questions or raise your hands during the meeting. And yeah, that's it. If you want to discuss anything, just write it in the chat or raise your hand at any moment. Yeah. So let's get started now. This workshop will be composed of two parts. They aren't equal in size or in time, and you will see that for yourself. So the first one will be a theoretical part where you'll get to go step by step to understand object detection and all the lingo around it. And then we will have a second part, which is an overview of a practical example, which is YOLOV5. So you will know more about it further ahead in the workshop. Let's start by the definition of object detection. So as you can read on the slide, it is a computer vision technique that allows a model to tell what objects are in an image and where they are located. So the first highlighted word is computer vision, and that actually means that object detection is part of the field that aims to give computers the ability to see. Did someone raise their hand? So no, the session isn't recorded, but we will have recording on YouTube anyway. It will be available in a few days at most. So we were saying that the first highlighted word is computer vision, and that means that object detection is part of the field that aims to give computers the ability to see, therefore the word vision. And that is by using any type of visual content, for example, images and videos. And then the second and the third highlighted words in the definition are what, and where. So it's going to tell us what objects are in an image, so recognize objects, but also localize them in an image, just like we can see in this example, where we have 4 boxes drawn around the places of the animals. And on top of each box, we have the label, so a dog or a cat, in this example. And now, when it comes to this slide, we have 2 different examples, but only one of them represents what we want from object detection. And so if we follow the previously mentioned definition, in object detection, we have information about what objects are in an image, and this information is actually present in both examples. The first image tells us that it's a plastic bottle, and so does the second one. But then, if we move to the second part of the definition, it tells us that we need to know where an image is, where an object is in an image, and this is only present in the second image. And if you're curious, the first example could actually be a case of image classification, where our goal would be to recognize what an image represents. Sorry, could you please?
Go ahead. Make some noise.
Yeah, you can continue. Kanja.
Can say you're talking on mute. I can't hear you.
Oh, did someone mute me? Can you hear me now?
Yes.
Could you please tell me when did the sound get cut?
think you were talking about image classification.
Okay, so I was saying that the first image is an example of image classification, and when you get started with computer vision, usually with computer vision and deep learning, you will get to classify images. This may be familiar to you, for example, with the cats versus dogs data set, or with the infamous MNIST data set where we have to recognize the numbers from 1 to 9, from 0 to 9 sometimes. And so you will notice actually throughout this workshop that we will go back and forth from classification because it helps us to understand detection better. And so now you could be wondering, why do we need object detection? Like, sure, it's fun to create models that detect animals or people or anything on an image, but what could be its applications? And so the answer is that there are many applications and many uses. The most famous ones are self-driving cars, video surveillance, and object counting. So for self-driving cars, you can probably guess that detecting cars and pedestrians around is more than necessary to avoid any type of collisions or accidents. With object detection, we can also it can also be easier and faster to follow people's movements in crowded places and make sure that every activity is normal. So, for example, we would make sure no one is stealing anything, no one is in need of any medical help, etc. But of course, you have to keep in mind, or you have to know that object detection is only the basis of these fields. So for example, when it comes to the second image with the video surveillance and the people, we are not only detecting people, but we are also tracking their movements. And this whole tracking movements is a whole other topic. But obviously, object detection is part of it. And one popular example that I wanted to mention today is an initiative by Amazon, and it's called Amazon Go, where the main idea is to have markets without any people or any help to scan the products or anything like that. So the idea would be that you walk into a store, you scan your phone at the entry, and then you will be tracked by hundreds of cameras that are set in the ceiling, and they are responsible for sending images of you, for example, taking products, adding them to your cart, and any other action like this. And then
Sorry, Kenzie, you've gone mute again.
here we are. Thank you. So I was saying that, once again, objects and person detection are only the basis of this whole concept. And we can see like this part of an image where the idea is you only scan your phone and you go into the market on your own, where there are other people shopping and stuff. You take whatever you want and you leave, and you will get the receipt on your phone. And this is all done thanks to object detection and tracking. And now we move to another point, which is the steps and the concepts that help us get started before diving into technical details. So we had an overview of what we want to achieve with object detection and why we need it. So now I would like us to go back, as I mentioned before, to image classification. So in image classification, we have an image, and we want to say what this image represents among a certain group of classes. So if we take this example, let's assume that we have plastic bottles and cans to recognize. And the goal is for each plastic bottle image to be recognized as class of plastic bottle, and the same with cans, with the class cans. And what we have as information is, of course, the image and the class each image belongs to. And this is also what we want to learn, our model to learn. But when it comes to object detection, we need another aspect, which is actually the most important one, and it is the localization of the objects. And the way we are going to do that is with bounding boxes. and their coordinates. So the bounding boxes are actually these boxes that we have seen in here, for example, and they surround each object that has been detected. And the way we are going to organize their coordinates is with minimum of 4 numbers. So we can represent them in 3 ways, usually. We would take 2 points, 2 edge points. For example, we would take the coordinates of the point in the top left and in the bottom right, or any others, and we would just any other 2 which are not on the same side, and we would simply calculate the others in our code. And then the second example would be to take 1 point of the edges, and then to have the information of the height and the width. And finally, we can also take the center, so the coordinates of the center xy, in addition to the height and the width. Sorry, sometimes I need to catch my breath with this heat. And so this is an example of a bounding box representation. In this case, it's using the center coordinates. So this is what a bounding box representation would look like. So the PC is the confidence score. So if PC, for example, is equal to 0.8, that means that our model is 80% certain that that the object is correct. And then X, Y are the center coordinates. H and W are the height and the width. And C1, C2, C3 is simply one hot encoding of the classes. So in this case, that means that we have 3 classes. And this is an example. So for example, if the second class is at 1, it means that the object we detected belongs to the second. Can we get
can I know what is the C1 series?
Sorry, I can't hear you very well. Could you please repeat?
I think probably what is it?
Class C1.
I'm so sorry, but I can't hear you.
Can you hear me? Yeah, hello?
That's why you change this thing now, the layout.
Can you hear me?
Yes, I can hear you. Now?
Yeah. What are those classes C1, C2, C3?
I can't hear you very well. Could you please type the question?
Yeah, classes C1, C2, C3.
Yeah, C1, C2, C3 simply represents the classes of the objects that we want to detect. So for example, if we want to detect dogs, cats, and rabbits, we would say that 100 is for cat, 010 is for dog, and 001 is for last animal, so which was rabbit. Is that clear?
So how you measure them, C1, C2?
It's not a measure, it's just a one hot encoding. So there are no measures in this.
Okay.
Thank
you.
You're welcome.
So this is a supervised learning.
Right? Yes, yeah, of course. This is supervised learning because we get as an input the images and the labels that go with them. So in this case, the bounding boxes.
Right.
Mm-hmm. Just give me a second. I'm just going to, I think we can take the questions here. So I'm just going to go to the top. Yes, you can get the slides with the YouTube recording, actually. I will see if I can send them as well. What is considered a reliable confidence score on this model? Do you mean like at what point do we say that this prediction is correct? If that is it, then it depends on your case, and then it definitely depends on your case and your data set. But of course, the higher it is, the better. How can we get bounding boxes? So to understand how we can get bounding boxes, we need to follow to the rest of the workshop.
Ken, I had a quick question here. So how many images you would require have a high confidence level that you can detect it, so that we don't want a overfitting scenario? So how do you do that? I mean, or do you have a specific number?
A specific number of what? Sorry, I didn't hear well.
Images be trained so that the model predicts accurately. Can you hear me?
Yeah, I'm just going to repeat the question to make sure that I understood. So how many images do we need to have to ensure that our model doesn't overfit and that it learns well?
Correct.
Yeah, that's it?
Yeah, that's it.
So once again, the more images we have, the better. And of course, they have to be when we have. Sorry.
Yeah, if it is more images, then their accuracy is better.
Yeah, but also if we have multiple classes, we need to have a certain balance between the classes. So we shouldn't have 80% of images that belong to one class, 10% to one class, and 10 other percent to the last class. This doesn't make sense. So all of these are actually characteristics of what makes a good data set.
Actually, I have one question. Can I ask?
For sure.
Actually, as you said, C1, C2, C3 is the classes. So if we have more number of, let's say, C1 class, so will it create a biasness in the model?
What would you create? So if we had more classes, we would simply have a longer vector in here. So it would be C1, C2, C2, C3, C4, and so on. So this only means that we have 3 classes. If there were C1 and C2, that means that we have 2 classes to detect. And if we had 80, then that means that we have 80 classes, C1 to C80.
Yeah, okay, fine. But I'm saying if we have a three images, let's say, dog, cat, and fox, and we have more number of dogs images in the training data set. So once we apply in the testing phase, so will it create a biasness in the model? Because we have,
of course. Yeah, of course.
So we must have, considerable amount of C1, C2, and C3, right? The right ratio of all these classes, right?
So if you have one class which is more than the others, of course it will be biased, and this is why we want our data to be balanced. Once again, all of these are the characteristics of what make a good data set.
Okay, fine. But are you talking about all these stuff, bounding box and all, during the training phase, right?
Yes. And they are also, this is the case which is presented in the slide is in the training part of the model.
Okay, thank you so much. Thank you.
You're welcome. So we can continue, and please, once again, just feel free to stop me at any time. We were talking about bounding boxes. We saw the many representations for them, and an example of what a vector of a bounding box would look like. And now let's go back again to image classification. So in image classification, let's just assume that our model makes a mistake during training. So when it is learning, it would, for example, detect the first image as a can instead of a plastic bottle. So in this case, it is pretty intuitive to kind of know that it made a mistake. And it simply has to do with the class. So if it predicted the wrong class, so if it's predicted the wrong class, we would say that this prediction or this detection is wrong. This classification is wrong. However, the problem now is how do we do this for image detection? Because we also have, in addition with the class, the bounding box. So how do we say whether this bounding box is good or not? So for example, we can have a larger bounding box in here. It would still cover a plastic bottle, but is it correct? And if it isn't, how would we measure this? And this actually takes us to a new concept, which is intersection over union. And this is what we're going to see. we have in this example 2 bounding boxes. The green one is the correct one, and the red one is the one that our model outputted at a certain point. So the question is, how do we say that this red one is wrong? Like, of course, when we see it, we see that the red one doesn't cover the whole car and it isn't as close to the correct one. But how do we see that in the code? And this is actually done with the concept of intersection over union, or also called IOU. The steps of it are pretty easy. So the first one is to calculate the intersection of the 2 overlapping bounding boxes. And then the second part is that we are going to calculate the union. And simply, we are going to do intersection over union of the 2. And so this means that we're going to divide the area of the intersection by the area of the union. And because the intersection is always smaller or equal to the area of the union, this value of IOU is going to be between 0 and 1. So let's see some examples, 2 examples actually. So the green one is the correct. Actually, it doesn't matter. Let's just calculate the intersection over union between these 2 boxes. So the red one and the green one. In this case, it's going to be about 1 out of 4. 1 out of 4. And this means 0.25. And in the second example, as you can see, this is closer to the correct one. It is going to be about 3 out of 4. And it gives us 0.75. So one conclusion we can take from these 2 simple examples is that the closer we are to 1, the better our bounding box is. And the closer we are to 0, the worse it is. And this is why we sometimes use these values for thresholds. So we say that if IOU is greater than 0.5, then our bounding box is decent. If it is over 0.7, then it is good. And if it is over 0.9, then it is great or even perfect. Yes, has someone raised their hand?
What's the process to obtain the initial correct bounding box?
Oh, so this is actually called labeling data. And the way we are going to do this is mostly manually. So you would take each, there are a few softwares that you can do this. For example, I think RoboFlow. Yes, I'm just going to give you the link in the chat. It's basically a tool that allows you to create bounding boxes and choose which representation you are going to write them in. So for example, YOLO or in RCNN, it depends. But you can check out this. I'm not sure if this answers your question.
Thank you.
Great. And so, yes, this is what intersection over union is. And now I want to give you a quick remark, which is that object detection is about finding what and where multiple objects in an image are. So this multiple keyword is actually very tricky for a model, and let's see why. Now, assume that we have to detect only one object in an image, never multiple objects. This way, what's going to happen is that we are going to have a model that will always output one vector, like the one we saw earlier. So the one with a PC, and then and then the bounding box, and then the classes. And this way, we know the dimension of the output of our model. But what if we had multiple objects? In this case, our model doesn't know how many objects are going to be outputted. And so we don't have the dimension of our output. And this is actually a key information for building a model. And that's the main or the core challenge of object detection. And this is where we are going to see some solutions for object detection and how they improved through time. So the first one, or actually the first ones, most of them, wanted to consider each image as multiple images. So we would consider one image as many. And the way we would do that, there are many ways. The first one was called slide-in windows. And basically, what we have is a box, as you can see on the slide, this green box. It's going to move through the image with a certain stride, so the step it's going to move with, and it has a certain size. And each part of the image it reaches is going to be processed on its own. So it's kind of, we have new images starting from a bigger image. And of course, you should note that this box that is moving is completely different from the bounding box. Let me know if there's any confusion, but the bounding box that we saw earlier localizes the object we detected. So it is the output of our model. And in here, the window, it's actually at the beginning, at the complete beginning. So it will tell us which part of the image we are going to process. Here is maybe a clear view of this. So we would take each part of the image that the window passes through, and we would do a classification to it. So classification is the simplest, kind of simplest computer vision task, where we would go to each image and say, which class does it belong to? So for example, if in here we are interested in car, so the first one isn't a car, so it's not going to output any object, not object, but any classification. And the second one, it's the same thing. In the third one, it's actually a part of the car. So maybe it's going to output a low confidence, because it's not the complete car. And this actually tells us about one of the limitations of sliding windows, or kind of obstacles, because we don't always know what size this window should be. And even if, let's just imagine we detected or actually classified this as car, and then we did the same thing with the front of the car, then we still have some pre-processing to kind of, post-processing to kind of organize the bounding boxes that we found. Does that make sense? All right.
I have one question. So like the sliding window protocol, we are telling that for the each and every frame, okay, we are doing the classification whether it's a car or not, okay. This is the one thing, and the second thing is that we are getting the parts of the car like the wheels and all, okay, the confidence would be low. So this is the two challenges, like the number of images would be more, and the second thing is also the confidence would be also less, so that we cannot identify what should be the exact size of the sliding window. That is the major challenges, right? Using the sliding protocol, right?
Yes, okay. Exactly. And this actually, just like you mentioned now, and this solution as a whole is actually very not exploitable, because it divides the image into way too many images. And that's actually its biggest disadvantage, is that it requires quite a lot of computation. So you can imagine that for each window or part of the image that we are going to process, we have one classification, so one convnet, and that's a lot on computation. So we prefer to improve the solution. And the way we can improve the solution, the first or most intuitive way, is to say, why do we have to go through all the image? What if we choose what parts of the image are we going to work on or to process? And so this is what region proposal stands for. So if we look at this image as humans, let's just imagine that we don't know that these are dogs, but even if we don't know what object this is, we still know that we have three parts in this image. So we have the grass behind, kind of the background, and then we have two objects. So two dogs, two objects that we can recognize as being two separate objects because of the way the textures and the colors, for example. And this is what we want our models to kind of recognize. We want models to detect the different regions that are in an image. And then after detecting those regions, we are going to do the classification. So instead of going through each window, we are going to choose the regions we are going to classify. Is that clear?
So how this region is basically identified? So like the sliding window we came to know, but this region proposal which we are telling it. So
yes.
Yeah.
And this is actually what we are going to see. The way we are going to use this or to do this is by using, for example, selective search. And the basis of this method, which is called selective search, is that we are grouping together the regions that are similar based on color, texture, size, and shape. And this actually can be done with CNNs. So as you can see in here, through few iterations, actually a lot of iterations, we can output exactly different regions of this image that we had in the beginning. Does that answer your question?
Yeah, could you please repeat once more? I didn't understand.
Yeah, of course. So the idea was that we need to find regions that we should classify instead of going through the whole parts of the image. And the way we are going to find these regions is by grouping together the parts of the image that are similar. So similar according to what? We can use, for example, color, the texture, the size, and the shape. So objects of same size, color, and texture are going to be grouped together. And this is what is done through selective search, for example.
Clear.
Yeah, great.
Hi. Sorry, one quick question.
Yes.
So you mentioned that you use CNNs to group the regions. I'm just quite not sure how CNNs exactly achieve, because in the end of the neural network we have the softmax layer. Let's suppose we're voice classification. So how do you section these? Regions. Just at a technical point of view, just wanted to.
Oh, actually, I don't have the details of how the network is constructed. I'm not sure I can answer this question right now. Sorry about that.
Sure, no problem.
Sure, thank you. And so after doing that, the problem with this solution was still that it's pretty slow. So why is it slow? Is that because before doing any classification or before finding out what our regions are, we have to go through this whole discovering regions and such. And this pre-processing takes a lot of time. And we still don't want that in our models. And this is why a new series of models came around, and they are called the RCNNs. And in RCNNs, we also use the same selective search, but with limited region proposals. So they would choose around 2,000 proposals at maximum, and with each region, we would do the same thing. So classification for each region, and then it would go around and around. No question? Sure. And with these families of RCNNs, so creating regions with RCNNs, there have been a lot of development in these series. And we had RCNN, fast RCNN, faster RCNN, and mask RCNN. And even though each one is better than the other, they all still have one common point, which is that they are what we call two-stage solutions. So why are they two-stage solutions? It's because they have one part which is about proposing regions, and then the second part which is about detection. And this whole process is actually heavy. So what we want instead of this is to have a one-stage process, or what we call a proposal-free solution. In proposal-free solutions, there are a few examples. We can find, for example, SSD and YOLO. And today we are going to focus on YOLO, actually. So YOLO stands for You Only Look Once, as you can see on the slide. And the idea behind this is that we omit the part of pre-processing and the part of region proposal. So we would feed our complete image, into our network, and we receive, by the end of it, the detections. And the way this is done, to understand the way this is done, we first have to understand what YOLO actually gives us. So let's go to the next slide. The idea is that we split our image into a grid of size S by S. As you can see in here, we divide this image into a grid of 3 by 3, so S is equal to 3. And another thing that you should notice is that we use the representation, in YOLO we use the representation of the center point. So we have confidence, center point, height, width, and then the classes. So in here we have 3 classes because we want to detect cars, buildings, and trees. And for example, let's just, in here we see that the yellow one detects the building, and it says that it's 0, 1, 0. And the one which detects the tree, it gives us 0, 0, 1. And so for cars, it's most likely going to be, it's obviously going to be 1, 0, 0. And so we said it has the center representation. And the first idea is that each cell of this grid will return a representation of one B-box. Why did they do this? So the first problem we started with was that our model doesn't have a fixed output. And the way YOLO are going to solve this problem is by saying that I am splitting my image, and each part of the image is going to give me one B-box. And in this way, we are actually fixing the output of our model. And how are we doing this? Let's see together. So we have 3 by 3 cells, so in this case 9 cells, and for each cell we have this vector, so one B-box, and this contains 8 informations, so it's going to be 3 by 3 by 8, and this is actually fixed. So we have solved the problem of the output size, of the output dimension. And so the way this works is that we detect the objects, and this sentence is going to be a bit tricky. And for each object detected, the cell which contains the center of this object will be responsible for representing it. So for each object that we detect, the cell that is responsible for representing it is the cell that contains its center. So if we take this as an example, let's assume we have detected this building, and we are going to see where the center of the building is. So it's in here, and this is the cell that is going to now represent the building. In these top cells, we don't have any objects that can be presented in here, so they are going to return a confidence of 0. And for example, in the car, the center could be here, most likely. Then it's going to be represented by this cell. And this is actually how YOLO works. And of course, we can see in here that there is, I don't know if you would have noticed, but for example, for this tree, the center of the tree is actually also in this cell. So both the center of the car and the center of the tree are in one cell. However, the cell can only represent one object. So how do we solve this? It's pretty intuitive. We're just going to represent 2 objects or more by cell instead of 1. So now the dimension of our the dimension of the output of our model has changed. So it's going to be 3 by 3 because we have a grid of 3 by 3, and 8 because that is the size of one bounding box representation, and 2 because we have 2 per cell. So this cell, which contains the center of the person and the center of the dog, can represent 2 objects. Is this clear enough?
No, can you please go to the last slide? So there we were telling like the 3 cross 3 it was there, okay, and the 8 we were showing it here, okay. So the 8 bounding boxes would be there. Why? Because we are having the these things, the 3 objects are there, detecting car, buildings, and trees. So 3 combination, 2 to the power 3, 8. We are getting it, right?
Could you please repeat the question? There's some points I didn't hear.
So
Sorry.
here, yeah, 3 cross 3 grid is there. Okay, so total 9 cells are there, and then we are saying that the 9 cells into the 8 bonding boxes would be there, right?
I didn't understand. I'm very sorry.
Yeah. So I'm telling that you are telling now 3 cross 3 into 8 here. In this
yes.
Yeah.
Yes.
How this 8 is coming, okay, and then how 8 cross 2 it is coming over there into the second example. Here how it gets.
All right. So I should re-explain the dimensions.
So dimensions like 2 to the power 3, 3 to the like the how we are getting.
Do you want me to explain like where does the 8 come from, right?
Yes.
All right. So the 3 by 3 is for the cells that are in the grid. So in this case, we have a grid which contains 9 cells, so 3 by 3. And each cell is going to output one representation of a B box. And this is what the representation looks like. In our case, we have 3 classes. So if we count in here how many information there are, we have 1, 2, 3, 4, 5, 6, 7, 8. And so this is where the 8 comes from. And in the second example, we have the 2, because we're not only representing one B box per cell, we're representing 2. So for example, this this cell is going to return 2 bounding boxes, this cell is going to return 2, and so on and so forth. And this is why it's multiplied by 2 in this case. Is it clear?
Actually, I have one question. Can I ask?
Yeah, just making sure that this was clear first.
Yeah, this is clear. But C1, C2. But in this image, we have only 2 class. One is girl and other is maybe the dog. So it should be 2 classes, C1 and C2. It should not be C3, I think.
Yeah, maybe if we had on these 2 classes only, but this is just an example because we don't know exactly how many classes do we have in general.
Okay, fine.
So if we had, but you're right, if there were only 2 classes, we would have in here, for example, 7. If we had 4 classes in here, that would be 9 information, and that's it.
So here, like for each grid, in the grid, each cell, since it is giving the 2 bonding boxes, okay, so it is having intersection over union kind of things, okay. So that's the reason we are getting it here, the 2 bonding box, okay. So this can be applied to the last images also, right? The last example also. So when the 2 bonding boxes we are getting it there also, we can get it 8 cross 2. Let's say here in this case, we want to identify let's say the building and the car is very near, okay. In the very last, okay. So here we are seeing it the 3, okay. So 3 bonding boxes are there into the 1, 2, 3, 4, 5. On the 6th cell, there is a 3 bonding boxes are there. 1 in yellow and 2 red, okay. So the 3, it should be shown here also, right? 3 bonding boxes here. Are you getting my point? So I
no, actually, very sorry. Could you please repeat the last part?
I'm telling that in this grid, okay. So you take it the middle row, the rightmost, middle row rightmost. So there are the 3 bonding boxes, right? So 1 is yellow and 2 red.
Yes, I understand. I understand what you mean. But we just mentioned that the cell which is going to represent the object is the cell that contains its center. So this red one, do you see this one? The center of it is actually in here, and it's not in here.
Okay.
So this is the cell that is going to be responsible for representing this car. But of course, if we needed more more bounding boxes, we can also have 3. So instead of 2 in here, we can also have 3.
So
sometimes we go.
So I'm asking the question. So instead of getting the bonding box for the cell, we are getting exactly how many bonding boxes it has covered, right? So what I'm understanding now, instead of having in the grid, there are 9 cells, okay. So irrespective of the cells here, the how many bounding boxes has been there. So that many, and how many bounding box it is there, that many the vectors will be given over here, right? That many vectors will be given over there. So in this case, 1, 2, 3, 4 are there. Only 4 are there. I'm able to see. So it has drawn 4 only.
I don't understand. Sorry, for what? Sorry. You mean 4 objects?
Yeah, only 4 objects it has identified, the 4 regions it has identified. Okay.
Yes.
Then
yes.
we are telling that the 8, we are telling that the 8 it has come, 8 bounding box it has come. But though it is just 1, 2, 3, 4 only.
I understand what you mean, but actually, the point you are talking about. So before having the image, the model doesn't know that it's going to output 4 bounding boxes. So we need a fixed size of an output. So even though these ones, so as you see in here, this one, all of these cells don't contain the center of any object. And so all of them are going to be 0 and then whatever other numbers, just to say that there is no object. It's just because we need a fixed output dimension, even though we're not going to use all of them. We may not use all of them, at least.
Okay.
And one other point I wanted to touch on is actually called the non-maximum suppression. And non-maximum suppression is actually a concept that we need in YOLO. The idea behind it is that sometimes our model outputs different bounding boxes for the same object. So we have this example where we have this person or this other person, which are represented each by different bounding boxes. So for example, in here, we have 3 bounding boxes, each with a different confidence score. And we need to organize this, or at least in this case, keep one of the bounding boxes, the correct one, or the most correct one. And the way we are going to do this is by using non-maximum suppression. The concept behind this is that we are going to take the most highly scoring bounding box. So in this case, it's the one with the confidence 98%. And we take the one with 80%, the one right below it, and we calculate the IOU between the two. And if this IOU is above a certain threshold, then we can remove the second one. And we do the same thing with all the bounding boxes for the same object. So in here, for example, with the 98 and 80, if we suppose that the IOU is above 0.6, then we are going to remove the second bounding box. And then we do the same thing with this bounding box with 98 and the one with 76. We calculate the IOU once again. And if it's above a certain threshold, we are going to remove the second one, so the one with the lowest confidence. And by the end, we are going to be left with only this bounding box. Is this clear enough?
Yeah, fine.
So in case of the image you had, like having 2 dogs in one image, will that complicate the situation?
You having what? 2 dogs?
Like you had 2 dogs in one of the images you had, right? 2 dogs in the same image. Will that complicate it? How you would detect it?
2 dots. What do you mean by 2 dots in the same image?
There was earlier in one of the slides you had an image which had 2 dogs.
Could you please? Was it in here?
I think one of the previous slides you had it.
You were detecting 2 dogs in one of the images. I think you should go.
2 dogs. I understand. Yes. So
the same frame. You should go back. In that same frame, there were two dogs, and you were detecting it. So will it create a problem if we are detecting same dog? 2 same dog in a single frame. Do you mean with non-maximum suppression in relation to non-maximum suppression? Yes.
Mm-hmm. So, for example, in this case, it's the same example. We have 2 persons. So if we try to calculate, for example, the IOU between these two, it's not going to be above a certain threshold. Actually, there is no intersection between them, so it's going to be 0. And that means that we are going to keep the 2. So there won't be any issue in this case. And same thing if we had, as you said, 2 dogs or 2 persons, we're just going to calculate the non-maximum suppression. And if it doesn't go over a certain threshold, then we keep the 2. And that means that we have 2 objects.
Yeah, then even the 98%, it's not necessarily always we get the 98%, right?
Yes, yeah, of course. But even if it wasn't about 98%, we're just going to, actually the way non-maximum suppression goes is that it goes class by class. So it goes through all the objects that have been detected as person. And in all of those, it's going to take the highest confidence with the one right below it and calculate the IOU, even though they are super far from each other in the image or something like that.
Okay.
Maybe I should try to write some kind of algorithm to explain it.
Sorry to interrupt, but could you please just repeat the last 2 minutes of what you said?
So I was talking about the way non-maximum suppression works exactly. So just give me a second. I think I'm going to write it. Yeah. So the way non-maximum suppression goes is that for each class, so for example, person, car, dog, it depends, we are going to take the highest scoring bounding box, and then we are going to calculate the IOU with the bounding box with the second highest bounding box, scoring bounding box. And if this IOU is above a certain threshold, so we choose it according to our scenario. If it is above a certain threshold, that means that they are most likely the same objects represented by 2 different bounding boxes. And so we are going to discard or to remove the second highest. And we continue to do this each time for all the objects detected for the class. So for example, if we had 100 people that have been detected, or 100 bounding boxes with the class people, we are going to do this. And of course, if the IOU doesn't, so else we're just going to keep both. This is actually what I said, and this is why I repeated it. Is it clear enough?
Yeah, thanks.
And so we were here, and now we can take a look at the YOLO timeline. So for YOLO, there have been a few versions. The first one was in 2015, and the most recent ones, so we're both in 2020 with a few months between them. The most popular one, I would say, is probably YOLOV3. But today we are going to take a look at YOLOV5 a little bit in details. So actually not too detailed, because this is just an introduction. So to stay in the scope of our workshop, we are going to go over the architecture, just the surface of it. So this is actually the architecture of YOLOV5. And you can see that it contains 3 parts. So the backbone, the neck, and the head. We are not going to go into detail, but we can understand a little bit of what each one does. So the backbone is actually used for extracting important features from input images. And for YOLOV5, we use CSV darknet. And then we have the neck. So the neck is the one that creates or generates feature pyramids. To give you an overview of what feature pyramids allow us to do, they allow us to detect objects at multiple scales. So no matter how small an object is in an image, this helps us kind of detect it. And finally, we have the head of the YOLO algorithm, the YOLO model, which is the last step. So in here, it has a YOLO layer. So it is the YOLOv3 layer. And its job is to generate the final output vectors. So in the dimension that we want. So I just took the same this example as sooner, but of course it can change depending on the grid we chose, the cells, the grid size we chose, and the number of anchor boxes or the number of B boxes we have per cell here. And so yeah, that is it with YOLO. And we are going actually to see an example. Just so I'm just going to Google, look for YOLOv5. So the first link you have is a link to the repo. And I advise you, if you want to take a look once you make progress in object detection, a little bit more into the details of the code if you want. What we are interested in today is just trying it out. So this is the official notebook of YOLOv5. We're first going to set it up. All right, so we just cloned the repo of YOLOv5 in here, and basically this is what it has. We're just going to try to go through a little bit. We have, so in here in utils, we have the needed functions. For example, we have activation functions, activations, the different techniques for data augmentation, for data loaders. We also have the metrics. And in here, for example, we can find the IOU. So IOU here. Yes, so VBox IOU. It's a little bit of a maze. You can also find the loss functions and all of this in utils. We also have the models directory where we can find all the versions of YOLO. So we have different versions of YOLOv5. The one we are going to use today is the YOLOv5S, and S stands for small. We are going to use the small one just because it's a little bit lighter and we're not going to have any weight in there. And of course, there are other larger versions. And finally, we have our data directory, and this is where we are going to have the files or the images we want to detect objects in. So just to let you know, YOLOv5 is pre-trained on the COCO dataset. So the COCO dataset contains over around, I think, 80 classes. So for example, we can see that there is person, there is Thai, there are other classes that you can find out on the COCO dataset link. I'm just going to delete this. And this is the entry point to use the script for the detection. So this simply displays the image, the result image. So in here, it says that we are going to use the YOLOv5S. Here it is. YOLOv5S, we are going to resize our images to 640 by 640. And this is the source where we are getting our data. So data images, here it is, data images. And we can see that it has two sample images in there. So we have this, the bus, the JPEG, and Sidan. And so this is it. Now we can try this. All right. It gives us a short summary of YOLOV5, so how many layers it contains and parameters. And we can see the results. I have an overview of the results of the images. So in the first image bus, it has detected 4 persons, 1 bus. In the second, 2 persons, 2 ties. And we can actually see that the results were saved in this directory. And we can try it out. So this is the result. You can find, as we said, the bounding box, the class, and the confidence score for each object. So we can check the same thing for the other image. And it's the same thing. We can also actually try an image of our own. I just picked an image beforehand. Here it is. So this is the image we are going to try. I just picked it from Google Images. And now that it's here, it is said in here that we can either specify the whole directory or a specific file. So we're just going to specify one file, which is bicycle.jpg. And here it is, the same summary, and it tells us that it has detected 3 persons, 3 bicycles, and 4 backpacks, and it has saved the result in exp2. So in here, instead of having exp, we're going to have exp2, and this bicycle. And so yes, this is actually the result of the detection with YOLOV5. It's supposed to be very accurate, and it can also be used in real-time scenarios. Where are you executing? So I'm not executing it. I'm just like using the pre-trained weights. So as you can see in here, we are loading the weights. So it has been pre-trained on, as I said, COCO dataset. So we're just using it. It would take a long time to redo the training. And is it what you mean? Okay, Google Colab. Yes, Google Colab. You just have to look for like YOLOV5, and it takes you to this collab. It is the official collab of the company that published it. How can we use this for a custom video? Actually, you can find all of this information. I think I'm going to leave. Yes, because we're done with this, but you can find all of this information in here. Yes, so they have a few tutorials where you can, for example, train on custom data.
How do you compare this with TensorFlow?
What do you mean TensorFlow?
That Google also has that. We can use TensorFlow to classify images, right?
Actually, it's not using TensorFlow to classify images. So, for example, TensorFlow or PyTorch are just frameworks that we can use. Okay. So it doesn't have anything to do in here. And of course, they are using a PyTorch in YOLOV5.
Okay.
Mm-hmm. And in here, they also use, we got a question like at the beginning of the workshop about labeling the data. They also use RoboFlow for labeling their images and videos, so video frames. Do you have any other questions?
The model is trained specifically for images, right? What type of images it is trained on? Do you know?
You mean YOLOV5?
Uh-huh.
YOLOV5?
Yeah.
Yeah, so it's trained on the COCO dataset. So I'm just going to look for it. All right. Okay. COCO dataset. Here it is. So this dataset contains, I said before, I think, 80 classes, and it is mainly used for detection and segmentation. it contains around 330k, 330k images, 1.5 million. Actually, you can find all the details in here.
Okay, good.
Mhm.
And in case I need to go for a text detection, this won't be helping, right?
Yes. Mhm.
If I want, my use case is a OCR, kind of like a detecting characters within the
Yes.
images, will this work for me, or only objects it can detect?
I don't think it would work for that, but I'm not really sure about that, to be honest. I don't know much about what did you say, character identification? I don't know.
Okay.
Can I answer this question about text classification?
Yeah, sure.
The thing is, over here you have your evaluation metric as an IOU. So basically what you're trying to do is you're trying to identify whether the block is the most overlapping to the ground truth or not. So the thing is, if you're trying to detect text and if you miss 1 or 2 pixels here and there, it is completely going to distort, some relevant information in your text. However, if you're trying to deal with the images of, say, dogs and cats, if you still miss like, I don't know, maybe like 5 or 10 pixels here and there, it wouldn't make a big difference. So I think it's
okay.
Oh, okay. All right. We also have another question about what is the output. So for YOLO, we have the center coordinates and height and width, if that's what you're asking about, Miriam. Yes. What is your question?
Yeah. Can I have a recorded session for this?
Sorry, could you please repeat? I can't hear you very well.
I mean, can I have a recorded session?
Yes, it will be available on YouTube in a few days.
Okay. Okay. Thank you.
You're welcome. Yes, again?
Yeah. How it is YOLO is different from SSD?
I haven't checked the details of SSD because I've never went into the details of it before, but I can see that maybe in a moment.
Okay, so if I want to implement this computer vision in Android application, is it possible? I mean, how we can implement it for object detection?
Apparently with YOLOV5 you can.
Which framework we can use?
I'm not really sure about that.
Is it TensorFlow Lite?
There
is one framework called TensorFlow Lite, so that can be used. TensorFlow Lite for object detection in Android. In Android platform. TensorFlow Lite.
So this isn't in relation with YOLOV5, right?
Using because ultimately they are detecting the object, so obviously TensorFlow Lite might be using this YOLO, maybe not version 5 but must be the older version.
Most likely, maybe yes.
Actually, if you go below down, there is one framework called TensorFlow Lite here.
TensorFlow Lite? Where exactly?
Yeah, go down. Yeah, here PyTorch Hub and below. PyTorch Hub and then below TF Lite. TF Lite.
All right.
This one.
Yeah, so this is what they use for mobile. Okay, it's nice.
Actually, a lot of customized data set can be used for detecting an object in Android.
All right, I see.
Yeah, okay.
I have one question, if that's okay.
Mm-hmm.
Is transfer learning really possible with YOLO?
I'm not sure, to be honest. I'm seeing in here that they talk about transfer learning with frozen layers, but I'm not sure what that means. I'm not sure what that means, to be honest.
I think it probably means you have a backbone in the network and you take the same backbone and retrain it for any other model, and you just keep everything the same. I think, not sure.
I'm sorry to tell you, I'm not sure either.
If I may explain, is that fine?
Sure.
I think it's transfer learning is basically to take a literal meaning of it, to transfer the weights, use the weights of pre-trained model. If we have the ImageNet data with millions of images, general images, if your data set is similar to that of ImageNet data like cats, dogs, cars, and all of these things, then transfer learning is you can freeze rather all the layers, and you can just use it for inferencing the data that you have. But if you have somewhat similar data with the model that was already trained on, then you can freeze the topmost layers and use the learning layers, the middle part of the network, in order for the model to learn your data. So it will sort of combine all those weights, and we can use it for inferencing. If the whole data is different, then you can use that whole network or the network in order to train based on your data. So there are basically four approaches, or it falls into four quadrants based on the similarity of data, based on the size of data. I think that is what transfer learning is.
I mean, yeah, I get the point what transfer learning is. My question was, other than keeping the network frozen, is there any other way to perform transfer learning? So the idea is, for example, in this network, you have you're trying to solve essentially two problems. One, what is the object, and two, where is the object? So what is the object? You can freeze certain layers if your task is very similar to some, say, ImageNet or something like that. I was more interested towards things that you can use to find where the object was by using transfer learning, and possibly something like a visual cue. That I think vision transformers do apply some sort of attention mechanisms, which tries to correlate objects. But I mean, yeah. So my question was more towards, I mean, can we do transfer learning on the localization part?
I think we can, if we try to just use the layers or the structure where it performs localization on, rather than the identification part. Not sure. I just use transfer learning on image classification, but not on object detection. But yeah, that's a good question. I guess we can explore more on that.
That was interesting anyway. So thank you both. I'm certainly going to look more into it as well.
I have one more basic question. Since you covered MS Coco dataset, I was more curious. So I was looking at some benchmarks on MS Coco dataset, and it seems that faster RCNNs perform so the idea is you measure these object detection algorithms on two different things. Number one, how good is your model, and number two, how fast is your model, which is the inference time. So usually if you look at these scores, if you just ignore the FPS per second, the RCNN models are actually better than YOLO. So my question is, why did you choose to present YOLO? Why not some SSD or some any other object detection framework, something maybe like a vision transformer or swim transformer? Why not? Why YOLO? Is there any?
Yeah, it was more of a personal choice, if we can say. But also after looking into it, I saw that a lot of people were interested in YOLO and especially with the YOLOV5. The thing with YOLOV5 is that there is no paper published and it hasn't been compared to the others, as you may know, but it's still kind of interesting and trendy. So this is why I chose it mainly. And I found the... And because the architecture of object detectors now all kind of look alike, so we have the backbone, the neck, and then the head, I just chose the one that I had more familiarity with.
Okay. One small thing to mention, a lot of people in the research community do not really agree with YOLOV5 because it came out from Ultralytics, if I'm not right. So, I mean, it's very similar to YOLOV4. If you slightly tweak it up, you can get...
yes. And there's like this whole conflict on the authors and such. Yeah.
Thank you.
Oh, you're welcome. So if there aren't, I'm not sure if I skipped any questions. Yes, Danny, like for OCR, your logic makes sense. And there is a question about tutorials for YOLO. I'm not really sure, to be honest.
What is the difference between OpenCV and YOLO?
Is there like an OpenCV module for object detection? Yes.
Yes, ma'am.
I'm just going to check what the OpenCV module for object detection is. I'm not really familiar with it. Anyone has used OpenCV for object detection before? You see some people used it. So I cannot really tell the difference because I haven't had experience with it. So I think we can pause the questions in here. Thank you all once again for your attention and for attending. Which screen am I now sharing? I would like to tell you a little bit about Code Labs Academy. Just let me know when. So, as you know, this workshop was brought to you by Code Labs Academy, which is an online learning platform that offers highly interactive learning. It offers actually a variety of learning methods, such as workshops and bootcamps. So when you enroll into a bootcamp, you get access to one-on-one career coaching on top of the access to the educational content. And you will also have the liberty of going through the learning content at your own pace. This workshop is actually one of, could give you a sneak peek of data science and the bootcamps of data science, which is actually one of the hottest tech topics nowadays. And of course, when it comes to the payment of the workshops, if you can't pay now, we offer a deferred payment schedule, and you can choose to pay our program tuition over 5 years with zero cost upfront. And if you choose to pay upfront, you actually get a 500 euros discount. And these are the details about our next session of the Data Science Bootcamp, which starts on July 9th. And the application deadline is on June 25th. And it's going to be a part-time format across 6 months. And so yeah, that's it in general. Thanks a lot for your attention, and
yeah, thanks. Quick question here. So, do you like, because everything is in euro? So, if audience is somebody from US, is that a possibility that we can enroll? Or?
Yes, of course. Actually, we have students from different countries, so it doesn't really matter.
Okay.
Because you study at your own pace and on your own time, this won't bother at all.
Okay.
Yeah, and
right.
Yeah, I have a quick question, Kenza.
Yes.
Thank you very much for this. Just a quick one, like, do you have like a GitHub or LinkedIn by which we could maintain touch with you?
Yeah, I'm just going to put my LinkedIn maybe in the chat.
Perfect. Thank you. Your stuff.
You're welcome. Thanks. Just a second.
Is YOLOV5
yes,
is used for the face detection, suitable for face detection or not?
Yes, it is. There is actually, you can find on GitHub different custom models which have been trained on faces. So you just have to train it on your custom data set instead of using the pre-trained one like I did in the example. Does that answer your question, Anil?
Okay, ma'am. Thank you.
You're welcome.
Have you tried training the model with custom images for this, or just use that?
No, I haven't tried YOLOV5 on a custom data set. Nope.
Okay.
Mm-hmm. So yes, thank you once again to all, and thank you for your attention. Maybe I'll see you another time. Goodbye.
Thank you.
Have a nice day.
Thank you, ma'am.
Thank you. Goodbye. Goodbye.
Thank you.
Goodbye.
Goodbye.